In part D, we'll talk about the final new transformation that we're going to be introducing, and this is horizontal shrinking and stretching. Again, to explain horizontal shrinking and stretching, we can draw a picture and then try to translate this algebraically. So let's go ahead and let our original function be called f of x, and this is again going to be our red function. And what we want to do is we want to compress the function f of x to be inside a smaller domain. So let's go ahead and let this green function represent f of x that's been compressed down. Again, let me reiterate that in this picture, the smaller graph is going to be equal to the red graph f of x. And let me go ahead and reiterate this. In this picture, our red function is going to be equal to our green function in the confined interval. And to see this, let's go ahead and label their domains. So we're going to call this starting point A. We'll call this endpoint, let's call this endpoint R, and in the middle, this is going to be B. And what we do know again is the function f of x on the interval A to R is equal to the function g of x on the interval A to B. So we can rewrite this sentence algebraically, and what this is going to translate to being is the following. Let me just write this in the right-hand corner. This is going to say that g of x is going to be equal to f and this is going to hold algebraically if we extend the domain of our function to the entire real line. So let's go ahead and write this down in the way that we've been writing all these transformations down. First, let y be equal to f of c times x. Then, if c is greater than 1, y, which is equal to f of cx, is obtained from f of x by shrinking the graph y is equal to f of x horizontally by a factor of 1 divided by c. And if we're given that c is between 0 and 1, then the function y is equal to f of c of x is going to be obtained from our function f of x by stretching the graph y is equal to f of x horizontally by a factor of 1 divided by c. So let's go ahead and look at an example. Example number 4. Given the function f of x, which is going to be equal to x squared plus x, let's go ahead and write an equation for the transformed graph that has been stretched horizontally by a factor of 10, and also shifted up sorry, let me say shifted 3 units to the right. Okay. So again, we're going to apply our transformations sequentially. So for step number 1, we just start with our original function, y is equal to an x squared plus x, and let's go ahead and stretch this horizontally by a factor of 10. And so stretching by a factor of 10, by the previous theorem, this is going to be equal to 1 divided by c. And so this is going to tell us that c should be equal to 1 divided by 10, which means that our new function, we're going to replace the x's with 1 divided by 10 times x. So this is going to become y is equal to 1 divided by 10 times x squared plus 1 divided by 10 times x. And now from here, we want to shift our graph 3 units to the right. And to shift our graph 3 units to the right, we're going to have to replace again our x values by an x minus 3. So before we do that, why don't we just go ahead and simplify what we have. This is going to be equivalent to being 1 divided by 100 x squared plus a 1 divided by 10x. All right, so moving on to step number 3. Our new function is going to be the following. Y is going to be equal to 1 divided by 100, and our x has been replaced by an x minus 3. And this is going to be our new function. Since we're already here, let's just go ahead and simplify this down. This is going to be equal to the following. And simplifying this one more time, we get that this is going to be 1 divided by 100 of x squared plus 4 divided by 100 of x minus 21 over 100.